This is the lesson for Thursday the 19th of January 2017, and to do just a quick recap of what we've covered already. We did normal approximations for chapter 5, and we had a look at the binomial and Poisson. Well, the binomial first of all, and we're going to look at the Poisson today. They're both discrete distributions, and we approximated them to the normal distribution, which is continuous, which meant that we had to have a continuity correction to do that. And that was like upper and lower bounds that we've looked at before. We then worked through some continuity corrections. We did a little bit of the exercise in 5a, and then we actually approximated the binomial to the normal. Moving on, we did the example, and we saw the conditions that we actually need for approximating the binomial to the normal, and that means that n should be large and p very close to 0.5, and that's what we saw with these figures here. We then moved on to another example, working that out, and then we also had to remember some of the normal distribution from S1 and drawn our tables and such like, and we worked out we had to standardise as well. So the key thing here is we've got a continuity correction, but then we had to change it to upper and lower bounds, and then we standardised it and then worked it out from the tables there. Another example was the binomial, where you actually have a success or a failure. So binomial meaning 2, so we've got a success or a failure, and we looked at this example where we had 50 yellow flowers, so that was n, so n was very large, and p was 0.7, it's close enough to 0.5. We did a little bit of calculation with that, and we also approximated it to the normal distribution by using the continuity correction as well, and we worked out the percentage error in that. I then asked you to do question 2. I think we may have finished that in the class. If not, I'll pop the answers at the bottom just now, so I'll just pause for a moment and then I'll do the solutions to those so that you can correct your own. So the numerical answers to question 2 at the bottom here, we've got a range, anything between those two, and then for B the same, and then for C as well, anything between those two. If we have a look at the questions, rolls a die 90 times, use a suitable approximation, the number of 6s. So again, we've got a binomial because a success is a 6, a failure is not a 6. It's 90 times, so that n is very large. So it does say there, and it would in an exam situation say suitable approximation. So you can see there, recognise it as a binomial and then approximate it to the normal. You can have a go at question 4, and then also question 5. You can see here we've got a multiple choice test. There are 4 possible answers to each question, given that there are 60 questions, so n's pretty big. Estimate the probability of getting more than 20 questions correct if it's chosen at random, and there's 4 available choices for each question. So even though there's 4 choices, it's either right or wrong for that one. Same here as well. 70 is pretty large. Suitable approximation. Estimate a probability of obtaining more than 45 heads. Fair coin, you either get a head or not a head, so that's your 2 options. So again, we've got a binomial distribution being approximated to a normal. So if you'd like to try those 3 questions, and I'll give you the answers for that. So if you pause this, just try it as a recap, and then I'll pop the answers on the page. So there's your full set of results for exercise 5B, your answers for 4, 5 and 6. So if you could check those, that would be great. Right, let's move on then. This time we're going to approximate the Poisson distribution by a normal distribution. And remembering that Poisson is a rate. Anytime you see a time scale of some sort, then lambda takes on that value. And what we get for the Poisson distribution is, if lambda is really large, then we can use that. And then we've got our expectation, our E of x, and our variance is also lambda. So there's no other way to think about the normal approximation, but you've just got to look at the mean and the variance. If they're the same as the original Poisson, then you can do the approximation. But there's no simple answer, as it says here, other than the larger the better, to the question of how large lambda should be before a Poisson can be used. So we'll have a look at a summary of this in a little while. So let's look at example 5 then. The random variable x follows the Poisson with lambda equals 25. So lambda is quite large there, so we can actually use a normal approximation. So if we think about it for part A, lambda is equal to mu, which is 25 from the Poisson, and sigma squared is also equal to lambda, which is 25. So that's actually equal to 5 squared. So we can say that x follows the Poisson of 25, and then if we change our variable to y, we can change that into a normal distribution of 25 and 5 squared. You can see your mu and sigma from there. So we apply the continuity correction. So apply continuity correction. And we get the probability of x bigger than 30 is approximately the probability of y being greater than 30.5. So we've changed discrete into continuous. Then if we standardise this, that's actually equal to z greater than, so that's using, remember that's using the standardisation of x minus mu over sigma. So that's greater than 30.5 minus 25 all over 5. So that gives us probability of z greater than 1.1. At that point you would draw your diagram, please. So take a little bit of space at the bottom and draw our diagram for that. So it would look something like that, using our normal distribution diagram. So from there we get it's equal to 1, which is the whole area. Take away everything below 1.1, so we can get that from the tables. So that's 1 minus 0.8643 from the normal cumulative tables, and that gives us 0.1357. So exactly what we were doing before, except we are looking for the Poisson distribution approximating to the normal. Let's do part B. And we've got it in between two values. So for part B, we've got the probability of x in between 18 and 35, and if we apply the continuity correction to that, then that's going to go to 17.5 and 34.5. If you've forgotten about the continuity correction, go back to your notes earlier in the booklet and you'll see what we need to do for inequality signs. We then need to standardise this, so that's going to be equal to standardise the 17.5, so we can use the tables. So 17.5 minus 25, and that becomes z because we're standardising it, and then 34 minus the mean, which is 25, and that's all over 5. Do that calculation, and that gives the probability standardised of minus 1.5 and 1.9. Okay, what we need to do now is actually draw the diagram again for the normal distribution. Where is that going to be? So I would always suggest drawing this, so it gives you a good idea what's going on. So minus 1.5 and 1.9. So the area that we require is in there, and the two values from the table that we're going to get there. So it's everything up to 1.9. Take away 1 minus everything up to 1.5. If that makes sense. So the two values that you need are 1.4713 plus 0.4332. So that part there is from S1, from the normal distribution, and you should be able to do that. So 9045. So you could probably do this on your calculator, but you're going to get some errors on that for the approximation, and in the exam you need to do the method marks for this one here. Right, look at example 6 then, that's the next one. A car hire firm has a large fleet of cars for hire by the day. Now that says to me straight away, by the day, and it's a rate of 21 per week. It's found that the fleet suffers breakdowns at a rate of 21 per day. So as soon as I've got a rate in there, I know that that is going to be the Poisson. Assuming that breakdowns occur at a constant rate, randomly in time, and independently of one another, use a suitable approximation to estimate the probability that in 1 week more than 27 breakdowns occur. So let's declare the variables then. So let x represent the number of breakdowns per week. So that gives us a rate. So x would follow the Poisson of 21, because we've got 21 breakdowns per week. So if we now change that, we can do the normal distribution. So y is going to follow the normal, and how does that work out? Well, that's going to be lambda is 21 and 21. Or I could put root 21 in there. It should really be root 21, shouldn't it? Okay, from that then, we can say that lambda is large, so we can actually approximate it, and it follows the normal distribution. So for the probability of x, the number of breakdowns being greater than 27, then that's going to be apply our continuity correction, so that's the probability of y going to be greater than 27.5. So that's the continuity correction, and then we've got to do our standardising. So that's going to be P, the probability of Z greater than, let's standardise it, 27.5 minus 21, and then remembering that we need square root of 21 on the bottom to standardise it. So that's all S1. Then using the normal for that is greater than 1.418. Drawing our normal distribution again. Just get an idea of what area that we're looking for. Greater than 1.418. And that would be the same as 1 minus the probability of Z less than 1.418, which is 1 minus 0.9222, and overall that's 0.0778. What you'll find with looking up the tables is that the nearest value for that 1.418 is actually 1.42. So the nearest value on the normal tables is 1.42, if you have a look for that. Right, what I'd like you to do then is on exercise 5C. I'd like you to do question 1, going right through to 5. And you can see from the questions in the exercise, it all mentions rates. So you should be able to do that okay. If you stop the video now and try that, and then I will put the solutions, or the answers anyway, for these just so that you can check. That should maybe take you about 15-20 minutes. So pause the video, do your solutions, and then I'll give you the answers. Well, if you manage to do those questions 1 to 5, then these are the answers hopefully that you should have got. If you look at the answers given there, there's a range, so anything between those two values are acceptable depending on what your roundings being, and the same here, and that's for the other parts as well. So if you just want to pause the video, mark your work, and then we'll get on to the last bit and finish this booklet completely. Okay, let's move on to which approximation should you actually use. And we've got a nice table here that takes you through it systematically of when you should be using what approximation. So we saw in booklet 2, section 2.5, that the binomial can sometimes be approximated by a Poisson distribution, and in section 5.2, in the previous lesson, we saw that sometimes it can be approximated by a normal distribution. The approximations that you need in S2 can be summarised with this diagram here. This is really quite useful. So on the left hand side we've got everything that is discrete, and on the right hand side we have got continuous. And if the approximation crosses the line that's in the middle here, a continuity correction is required. So if binomial is going to Poisson, they're both discrete, so there's no continuity correction. But if Poisson goes to normal and binomial goes to normal, then you need a continuity correction. To go from binomial to Poisson, large n, small p, and let lambda equal to np. From normal, binomial to normal, we looked at that last time, where we have mu is equal to np and sigma squared is np bracket 1 minus p. And that's when we said when we've got a large n and p close to 0.5. If we've got a large lambda, then Poisson can be approximated to a normal, and we get both our values, lambda equal to mu and sigma squared. So that's actually quite a nice summary of what we've done so far. Then you've got to be able to identify that in exam questions. So if you're approximating a binomial distribution to a normal distribution, you should always go directly to the normal distribution and not via a Poisson distribution, as this involves one, not two approximations, and should therefore be more accurate. So you want to do one approximation if possible. Don't go around the everything else to get to the answer. So for the binomial distribution, there are two possibilities. There's two approximations, depending upon whether p lies close to 0.5. If it's close to 0.5, we use the normal distribution, or p is small, in which case a Poisson distribution is used. If you're in doubt over which approximation is appropriate, a useful rule of thumb, so a useful rule of thumb is to calculate the mean NP, and if this is less than or equal to 10, use the Poisson tables. So you can use the tables because it just goes to 10. If the mean is more than 10, then it's the normal approximation is what we use. Okay, so that's quite a good bit to know there. Do that in red, you can see. So that part there helps quite a lot, along with the diagram that's up above. Let's apply these rules or this schematic diagram and see if we can apply it to the next example. Example 7. A spinner is designed to land on red 10% of the time. Use suitable approximations to estimate the probability of A. Fewer than 4 reds in 60 turns of the spinner. B. More than 20 reds in 150 turns of the spinner. Well, let's declare our variable to start with. So for part A, if we look at it, let x equal the number of reds in 60 turns of the spinner. So x would follow the binomial n is 60 and 0.1. Okay, so that's n and p. And we get the 0.1 from our 10%. So, if we calculate the mean of this binomial, or the expectation, we can see which one to use. So, if we do E of x, that's n times p, so it's 60 times 0.1, which is equal to 6. Now from our paragraph from before, it says if the mean is more than 10, then the normal approximation is usually suitable. So this is less than 10. So that tells me that I should be using the Poisson distribution. So this is just something that you've got to learn with this. So therefore, x can be approximated to a Poisson of 6. So we can go straight from the binomial to the Poisson rather than the normal. So we don't have to do any continuity correction at all. So the first one is a probability of x being less than 4 reds, and that's going to be the same as the probability of x less than or equal to 3. So we just have to go to the Poisson table with lambda is equal to 6 and x equals 3, if you can look that up on your table. the Poisson table, please, and that should come up with 0.1512. Moving on to part B, we've got more than 20 reds in 50 turns. Okay, let's declare our variable again. So let R equal the number of reds in 150 turns of the spinner. So this time the variable R is going to follow the binomial because it's red or not red, and it's going to be 150, n is 150 this time, and it's still a red is 0.1 and not a red is 0.9. So if we work out the mean for this one, that up. So the expected value of R is still n times p, which is equal to 150 times 0.1, which is equal to 15. Now 15 is greater than 10, therefore we'll use the normal approximation. Now that means that sigma squared is going to be 150 times 0.1, which is times 0.9, which is equal to 13.5, and we also need the continuity correction as well. So x is approximately following the normal distribution of 15 and the square root of 13.5 squared. So we get the mean and the variance. So we've got to do a continuity correction, so we want the probability of R greater than 20. So our continuity correction gives us the probability, we'll change R into Y, that's greater or equal to 20.5. And then we've got to standardise it now. So let's standardise this. It becomes probability of Z greater than, remember it doesn't need to be greater or equal to because it means the same thing on a continuous distribution. So 20.5 minus 15 over, so we've standardised it now. And then from there we get probability of Z greater than 1.496, etc. Now on the tables, the closest value that we'll get for this on the normal tables is Z equals 1.50. So you look at, if the value's not there on the table, then you look for the closest one to it. So looking at our distribution, we're looking at 1.50 and it's going to be greater than, so it's going to be probability of, so it's 1 minus the probability of Z less than 1.50. So that's our S1 again using our normal distribution. So 1 minus 0.9332. So look your tables up for 1.50 on your normal distribution, and that gives us 0.668. So that's the probability of more than 20 reds in 150 turns of the spinner. Very small chance that. Okay. Right, what I'd like you to do then is to finish this booklet completely by doing the mixed exercise. And that's 5D. And I'd like you to try questions 1 to 5. Now the solutions to these are in the S2 booklet. If you go into my room, there's one on the shelf. You can help yourself and have a look at that. I think Magomed, you might have one already, so you could share the answers on that. And what I'd like you to do is finish that for next Thursday, which is Thursday the 26th of January. So finish for Thursday 26th of January, and we'll have a look at them. If you've got really stuck on that, we can have a look at it on Monday. Okay.